Okay, everyone, welcome to chapter 12, which is exciting because this is our last chapter of the course. So, very excited for you. You're almost there. So let's get into 12.1. So we're going to talk about linear regression and correlation. And the objectives of this chapter are basically we're going to introduce the concepts of linear regression and correlation, and then we're going to talk about line of best fit, how to create one, what is it. Then we're going to talk about the correlation coefficient, and then finally we will deal with outliers. Okay, so 12.1 is a little bit of a review. I don't know when was the last time you had algebra, but I'm sure somewhere along the way you've had it at some point in time. So linear regression for two variables is basically has to deal with lines, right? So it's based on a linear equation. So you might remember the form y equal mx plus b, where m is the slope and b is the y-intercept. Well, in this textbook, they introduce it as y equals a plus bx, which is exactly the same thing, except that the constant comes first. So the y-intercept is a, and the slope in this case is b. Okay, so just remember that, the coefficient of x, the number that goes right in front of the x is the slope, or the rate of change, and the constant is a number that has no x attached to it, right? It's a constant number. These variables are what we call dummy variables. It could be anything. It doesn't really matter. Okay, well, so where x is the independent variable or the input and y is the dependent variable or the output. So usually what we do is we introduce a value for the independent variable and then out comes the dependent variable. So here's some examples of linear equations. So we have here y is equal 3 plus 2x, or y is equal to negative 0.01 plus 1.2x. It could also be in a different order, like y is equal to 4x minus 7, or y equal to x. Or, it's just, there's so many different combinations. But the one thing that they will always have in common is that y is raised to the power 1. There is no exponent here. I mean, there is one technically, an invisible 1. And so is x, there's an invisible 1, but there is no, it's not squared, there's no cube, there's no tiny powers of x or y. And the other thing that these all have in common is that they form lines, okay? So the graph of all of these equations is going to be a straight line. So any graph that is not vertical can be written in this form. And why do we have to say that? It's because the vertical lines are of the form x equals a number. Okay, so the strictly vertical, the equation is x equals a number, but we're in stats, we're not really going to talk about that. That's a conversation for another class. So let's see here, what if we want to graph the equation y is equal to negative 1 plus 2x? So remember that negative 1 is the y-intercept, so it actually would intersect the y-axis somewhere down here, and then it would go up 2 over 1, up 2 over 1, so that's the slope. 2 is considered the slope, the rate of change, the behavior of the line. It tells us how far up it goes, whether it increases or decreases. You can think of a hill, and if there's upward slope and there's downward slope, right? Okay, so let's see here. Let's do a super fun example. So Aaron's word processing service does word processing. The rates for services is $32 per hour plus a one-time charge of $31.50. So the total cost to a customer depends on the number of hours it takes to complete the job. So let's find an equation that expresses the total cost in terms of the number of hours required to complete the job. So now we have a way to describe how much they're going to charge a customer, right? Now, if we let x equal the number of hours it takes to get the job done, and y equal the total cost to the customer, well, let's think about that. $31.50 is a fixed cost. That means you only pay it one time. So even just by, having their services, you have to pay $31.50. But however many hours it takes to complete the job, you have to pay $32 per that hour. So the expression 32x represents the cost for the services, okay? So together, the total cost is going to be y is equal to the fixed cost of 31.50 plus 32x. So now if you say, okay, well, my job took 2 hours, you would plug in 2, you would get 32 times 2, 64, and then you would add that to 3150, and you would get the total cost. Okay, so let's talk a little bit about behaviors of lines, and how can you tell if a line is going up, going down, or stays the same. So if you have an equation y equals a plus bx, in this case, the slope is b, right, because it's attached to the x, and a is the y-intercept, in other words, where it crosses the y-axis, okay? So if you remember from algebra, slope is a number that describes how steep a line is, and the y-intercept is the coordinate of the point where the line crosses the y-axis. Okay, so here's some 3 possible graphs. If the slope is positive, the line increases upward, going from left to right. If you look at it, it's like you're going up a hill, right? So that's a positive slope. You're going up. If there is no slope, 0 slope, then you're basically, there's no change, okay? And so you're just going straight. It's just a horizontal line. It's not very interesting. Now, if you have a negative slope, that means that you're going down, okay? Your line is going down and decreasing as you read it from left to right. Okay, so let's do another super fun example. So Svetlana tutors to make extra money for college. For each tutoring session, she charges a one-time fee of $25 plus $15 per hour of tutoring. A linear equation that expresses the total amount of money she earns for each session she tutors is y equals 25 plus 15x. So what are the independent and dependent variable? What is the y-intercept and what is the slope? Can you interpret them using complete sentences? So if I were you, I would push pause. I would try to just talk it through and then read the rest of this, whatever. So I'll give you like 5 seconds. Okay, great. So if you said that the independent variable x represents the number of hours she tutors, you'd be correct. The dependent variable would be the amount that she earns for each session, right? And the y-intercept in this case would be 25, right, because it's by itself. And the slope would be 15 because that is the rate that she charges per hour. So for every session, she earns $15 for every hour that she tutors. And that's it for 12.1. This video actually has both 12.2 and 12.1 together. Exciting for you. Okay, so 12.2 talks about scatter plots. So before we even get into regression and correlation, we need to be able to describe this way of graphing that shows the relationship between x and y. And the easiest way to do this is a scatter plot. So let's listen very carefully because this is super easy. If you get it the first time, you're going to be pro. So, okay. So in Europe and Asia, m-commerce is popular. So we have, what is m-commerce? They use special phones that work like wallets, and they provide phone and internet service. So now we have smartphones, so it's kind of like, this is old. But users can do everything from paying for parking to buying a TV set or soda to banking to checking sports scores. And for the years 2000 through 2004, was there a relationship between the year and the number of users? Let's construct a scatter plot. So here we have the data. Of course, this is statistics. We're all about data. So X represents the year. So we have 2000, 2002, 2003, 2004. And let Y equal the number of m-commerce users in millions. So in the year 2000, there was 500,000. In excuse me. 2002, there was 20 million. 2003, 33 million. 2004, there was 47 million. So here's the table. And if we let this is X and this is Y, and if we were to create a beautiful graph and just plotted these as points, see here I have my graph. This is 2000, 2002, 2004. I have at 2000, it's 0.5. So it's so very close to 0. Okay, so let's say the highest point on my y-axis is 50. So at 2002, there was 20 million, so it's about here, less than half, just a little bit. At 2003, which would be in between 2002 and 2004, of course, the number of users is 33 million, so it would be a little higher. And then finally, at 2004, the number of users is 47, and as you can see, it's very close to the 50 mark. So how would we use this? I know you guys are waiting so eagerly to learn. How would I use this? How would I do this with a calculator? So let me show you. If you want to create a scatter plot, you have to first enter your data into L1 and L2. By now we're pro at this, so I don't need to go over this too much. Once you do that, you hit second and then go to the Y equals, and that'll give you the stat plots menu. Then you hit enter to enter number 1. Make sure that the others are all off. Okay, you hit 1, and then you see you can turn it off, so you click on that. And the type is the first one. That's the scatter plot one. It might be on any of the other ones, but make sure you're on the first one. X list is L1, Y list is L2, and then you can choose whatever mark you want for the points. Then you just hit graph. And there it is. Now, if it doesn't, you don't see it right away, you could hit zoom 9 for zoom stat, and then it'll fit the window. Okay? So that is how to create a scatter plot on your calculator. All right, so let's say a little bit more about scatter plots. Okay, so what's the point of having them? The nice thing about scatter plots, the more and more data you have, oftentimes there'll be some kind of relationship. You'll see a direction, okay? Not always, but sometimes you'll see it, and it's really exciting because you can use this kind of relationship to create a function to approximate where the data could go. And in a very real way, we actually can kind of, for lack of better words, you could predict the future almost, okay? You can almost predict where it's going to go next. So it's very exciting. And this phenomenon is used all the time. I mean, we're talking in weather, you know, we try to predict everything using data. So it's very exciting. So here we go. So how do we tell if there's a clear direction? Okay, so let's say if you have high values of one variable occurring with high values of the other variable, or low values of one variable occurring with low values of the other variable, that would be the case of a positive linear pattern. So see here, if this is the x value, this would be a high value over here, right? Of course, this is 0, 0. And then high values would be up here. So if I had my scatter plot where kind of the data was here, and then when it was low, they were both low, you could kind of see that it's increasing over time, and that's called a strong linear pattern if that's always the case. And another way to determine a direction, a linear, if we're trying to approximate a linear relationship, of course, if you have high values of one variable occurring with low values of the other. So in this case, notice that for the y-axis it's high, but for the x-axis it's low because it's in the beginning of the x direction. And then down here, it's a low value for the y-axis, but it's high for the x. So if you can see for yourself that they kind of go in this almost linear pattern, right? But it's very close. So we call this a positive strong, and this is negative strong linear pattern. And why would we call this positive and this negative? Well, because here it's increasing, right? So if I was to draw a line to approximate this, it would be a line with a positive slope. And then in this case, it would be a line with a negative slope, of course, because it's decreasing. Now, we can determine the strength of a relationship by looking at the scatter plot itself and seeing how close the points are to either a line, a power function, an exponential function, or some other type of function. Now, in this chapter, we're focusing mostly on lines, but all this other stuff is possible, and in fact, it's very interesting. I mean, I'm looking at this daily, actually. There's some stuff that I still look at that's very interesting. So for a linear relationship, however, there is an exception. Okay, so the only exception would be if all the points fall on a horizontal line, then that would show no relationship. Okay, so when you look at a scatter plot, you want to observe the overall pattern and any deviations from the pattern. And so let's look at these scatter plot examples. So here for the first one, you notice that there's a strong positive linear pattern. This one has, B has a linear pattern but with one deviation. You see this one over here, it's not falling in line. This one on the right, the third one from the top, A, it's an exponential growth pattern. Okay, and it goes up in an exponential way. This one goes down in a negative slope pattern. And then this one looks like a negative linear pattern, but it's weak because they're not, it doesn't look like a straight line. And then this last one, of course, there's no pattern. Look at it. Can you even approximate? Does this even look like a function? No, it does not. Okay, so, so finally, we're going to continue talking about linear patterns for the rest of this chapter. So like we said, it's strong if the points are close to a straight line. If we believe that scatter plot shows a linear relationship, we want to draw this specific line, and this line can be calculated through this process called linear regression. However, we only calculate a regression line if one or more of the variables helps to explain or predict the other variable. So if we have x be the independent variable and y is the dependent, then we can use a regression line to predict y for a given value of x. So that's very exciting. So I will leave you with that thought. And your super fun homework is here, 12.1, practice 1 through 16. And then 12.2 is 17 through 19. Congratulations, good luck, and happy studying, and I will see you on the next video.